Today, we're going to dive into a really powerful concept, one that goes way beyond just being resilient or tough. We're talking about a way for things to not just survive chaos and uncertainty, but to actually get stronger from it. This is all about the science of gaining from disorder. So, let's start with a question. What's the opposite of fragile? Now, you're probably thinking of words like robust or strong, right? But think about it. Those things just resist shock and stay the same. The true opposite of fragile doesn't just resist damage, it's actually transformed by it, for the better. And that's a pretty wild idea. And this chart breaks it down perfectly. On the left, you've got something fragile, like a wine glass. It's harmed by disorder. You drop it and poof, it shatters. In the middle, you have something robust, like a brick. It resists disorder. You drop it, nothing really happens. But on the right, that's where the magic is. Antifragile. Think about your muscles. When you exercise, that stress, that disorder doesn't just get ignored. It actively makes the muscle grow stronger. It literally gains from disorder. Now, this isn't just some catchy phrase. Antifragility is a precise mathematical property. It's a characteristic of systems that genuinely improve. They increase their capability when they get hit with stressors, shocks, and all sorts of randomness. And because it's a real property, we can actually identify it, we can measure it, and this is the exciting part. We can start to design systems to have this incredible ability. Okay, so how do we actually see antifragility in action? Well, the key is to look at how a system responds to stress. If you plot it out, you get a response curve, and it really all comes down to the shape of that curve. First up, we have what's called the frowning curve. This shape, which is mathematically concave, is the signature of a fragile system. You'll notice how the curve gets steeper and steeper. That means as you add more stress, the harm doesn't just add up, it accelerates. A little more stress starts to cause a lot more damage, until, bang, the system hits a breaking point and fails completely. But then, you have its beautiful opposite, the smiling curve. This convex shape is the telltale sign of an anti-fragile system. Here, the response to stress isn't just positive, it actually accelerates. The more volatility and stress you add, the system doesn't just get a little better, it starts improving at a faster and faster rate. This is the secret sauce right here. All right, so this isn't just some abstract theory. This idea has profound real-world applications. And to see just how powerful it is, let's look at a really counterintuitive example from the world of medicine. So let's imagine a cancer treatment. We've got two different ways to give the medicine. One is a steady, even dose, 100 milligrams, then another 100 milligrams. The other is uneven, it's volatile. A big blast of 150 followed by a smaller dose of 50. But here's the crucial detail. Look at the total dose. It's exactly the same in both cases, 200 milligrams. So the big question is, which one works better? You know, your gut might tell you that since the total amount of the drug is the same, the results should be the same. But if we remember the secret of that smiling curve, we get a very, very different answer. And here it is, the aha moment. It turns out the way many cancer therapies work follows a convex smiling curve. That massive initial dose of 150 milligrams can overwhelm the tumor's defenses in a way that a steady dose just can't. Because of that curve shape, the huge benefit you get from the high dose more than makes up for the smaller effect of the low dose. So the average outcome of that volatile, uneven schedule is actually way better. By embracing that volatility, the treatment becomes a whole lot more effective. Amazing, right? Now, this principle doesn't just work on a tiny cellular level. We can see it on the biggest scale you can possibly imagine. So let's zoom out from the microscopic all the way to the planetary and see how Earth itself actually has these same properties. This brings us to something called the Gaia hypothesis. And the idea here is to think of Earth not as just a static rock flying through space, but as a single, dynamic, self-regulating system. Life doesn't just passively adapt to the planet. It actively shapes the planet's conditions to create an environment that's even better for more life. It's a massive feedback loop. And this connects directly to antifragility. I mean, just look at our planet's history. These huge planet-wide stressors, we're talking ice ages, massive shifts in the Earth's orbit, they weren't just disasters to be survived. They were catalysts. These shocks drove incredible bursts of evolution and forced the entire system to reorganize itself. The planet didn't just survive these shocks, it became more complex, more diverse because of them. So let's boil this all down to a simple 3-step recipe. First, you look at a system and how it responds to stress.
Second, you figure out the shape of that response curve. Is it a fragile, frowning curve or an anti-fragile, smiling curve? And finally, step 3. If it's smiling, you know that you can actually use volatility and randomness to get a better result.
Which brings us to a really fascinating final thought. Antifragility isn't just a cool philosophy. It's a real, measurable, and even engineerable property. Now that we have a way to understand things that gain from disorder, the real question is, where should we build it next? In our economies, our personal health, our education systems? Suddenly, the possibilities are absolutely everywhere.